Hello. We will start Unit 4 of our course with the study of capacitance of a conductor. What is the meaning of capacitance of a conductor? Well, tell me, what is the meaning of capacity of a container? This is a container, it has a capacity. I know most of you will understand it as capacity of a container is the amount of substance it can hold. Now, I'm going to define it in a slightly different way. When I pour some liquid or whatever that is into this container, what happens is the height of the liquid in the container increases. Now, when I poured liquid into it, its height is now this much. Now, if I pour more liquid, the height increases. So, as I keep on pouring the liquid, the height of the liquid inside the container increases. So, I'm going to define capacity of this container as the amount of liquid that will raise the height of liquid in the container by 1 meter. How much liquid is needed to raise the height by 1 meter? In other words, you keep on adding the liquid, you keep on increasing the height. That means the effect of adding the liquid is to increase the height. And so we define capacity of that container as the amount of liquid that will increase the height by 1 meter. In the same way, we can define capacitance of a conductor. Now tell me, when you give charge to a conductor, what are you raising? In the case of the container, when you put liquid inside the container, you raise the height. When you give charges to a conductor, you raise its potential. You see? Do you remember the equation for potential of a charged sphere? It is kq over r. You increase the charge, you increase the potential. So, when charges are given to a conductor, it raises the potential of the conductor. As a conductor gets charged, its potential increases. Therefore, how can we define capacitance of a conductor? The amount of charge given to a conductor to increase its potential by 1 volt is called the capacitance of that conductor. So, in the same way as when liquid is poured into a container, the height increases. When electric charges are given to a conductor, its potential increases. The amount of charge that is given to a conductor to increase its potential by 1 volt is called the capacitance of the conductor. Now, we use the letter C, uppercase C, to represent capacitance. Now, what is the unit for measuring capacitance? If you look at the definition, you can figure out the unit right away. It is the amount of charge per unit potential difference. The amount of charge needed to raise the potential by 1 volt. It is coulombs per volt. Is that right? That is the unit of capacitance. Since capacitance is charge per unit volt, we can write an equation for capacitance of a conductor. Capacitance of a conductor is Q divided by V, the amount of charge needed to raise the potential by 1 volt. Charge per volt. Since Q is measured in coulombs and V is measured in volts, capacitance C is measured in coulombs per volt, and it has a meaning, it has a name. coulombs per volt is called a farad. You see, just like a coulomb is a large unit, farad is also a very large unit. That means for utility purposes, for everyday usage, you've got to use smaller units. What are the smaller units? Microfarad, which is 10 to the negative 6 farad, nanofarad, 10 to the negative 9 farad, picofarad, 10 to the negative 12 farad, and so on, are the commonly used units of measuring capacitance. Now tell me, what is the potential of a charged spherical conductor? We talked about it last class also. The potential of a spherical conductor is KQ over R, and if you replace your K by 1 over 4 pi epsilon naught, I hope you know that. K is 1 over 4 pi epsilon naught. I can write the potential of a spherical conductor is Q over 4 pi epsilon naught R, and therefore can you write an expression for the capacitance of a spherical conductor? What is the definition of capacitance? Capacitance C equal to Q over V. So capacitance C equal to Q over V. For a spherical conductor, this V equal to this quantity, Q over 4 pi epsilon naught R. Let's replace this V by this quantity. That gives me the capacitance of a spherical conductor is Q over 4 pi epsilon naught R. And you can see the 4 pi epsilon naught R will go up. Q and Q will cancel. That will be 4 pi epsilon naught R. What does that tell you? Capacitance of a conductor does not depend on the amount of charge or the potential. You see that? In the same way, if you look at this one, what does the capacity of this container depend on? The capacity of the container depends only on its physical dimensions. In fact, if I increase the diameter of this container, I increase its capacity. In the same way, capacitance of a conductor only depends on its physical dimensions. The capacitance of a conductor does not depend on the amount of charge you put in or the potential difference. You see, you increase the potential difference, you increase, if you increase the amount of charge, the potential difference also increases. That means Q over V will remain a constant. Capacitance of a conductor is actually a constant for a given conductor. It depends only on the physical dimensions of the conductor. What does the capacitance of a spherical conductor depend on? It depends on the radius of the conductor. That means if you take a conductor, well, this is not a conductor. Suppose you take a conductor, a spherical conductor of given radius, its capacitance is a constant. It means the amount of charge that this will hold so that its potential is increased by 1 volt is the same. The capacitance of a conductor does not depend on the amount of charge you put in it. Okay. What is a capacitor? Well, so far we talked about capacitance of a conductor. Let's now talk about a capacitor. Alright, let's consider a conductor carrying a charge Q. Now, if a conductor is carrying a charge Q, then it has a potential V. Therefore, its capacitance can be written as C equal to Q over V. This conductor carries a charge Q. When a charge Q is given to it, its potential is raised to V, so that its capacitance C equal to Q over V. Now tell me, is it possible to increase the capacitance of this conductor? Well, you know that capacitance is Q over V. If by any means I can reduce the potential of that conductor without changing the amount of charge on it, that means in order to increase that potential back to the original value, I then need to put more charge in it. Now, in doing that, I am raising the capacitance. So, if you want to increase the capacitance, try and lower the potential of the capacitor or of the conductor. Now, can you suggest a way we can lower the potential of a conductor? This conductor now has a positive potential V. How can you reduce its potential without reducing the amount of charge on it? Well, try this. Bring a neutral conductor near the charged conductor. What happens when a neutral conductor is brought near a charged conductor? We talked about this some time ago. When a neutral conductor is brought near a charged conductor, polarization of charges will take place inside the neutral conductor. Now here I brought a neutral conductor. This is a neutral conductor. But the moment you bring a neutral conductor close to this charged conductor, what happens is inside the neutral conductor, polarization of charges will take place. What is polarization? Negative charges will move so that they reside close to the positive charged object. That means leaving the other end positively charged. You have a split of charges in the neutral conductor. As a result, the influence of these negative charges are going to be felt on our charged conductor. You know that the potential of a negative charge is negative. So, the presence of these negative charges will produce a negative potential on our charged object. The negative charges in the neutral conductor move so that they reside closer to the positively charged conductor, making the end of the neutral conductor near the charged conductor negative. You see that? Now, the accumulation of these negative charges near this positively charged object reduces the potential of this, reduces its positive potential. I suppose you can understand that argument. That means we haven't changed the amount of charge on this charged object, but by simply bringing a neutral conductor near it, we have reduced the potential. The V is now, if V prime is the new potential of this conductor, that V prime is less than the original V. That means if you now want the potential back to V, we now need to add more charges. That means we have now increased the capacitance of the conductor. Now this decrease in potential of the charged conductor without changing the amount of charge on it causes an increase in its capacitance. That means now it can hold more charges at the same potential. You see that? So we have increased the capacitance. Now, is there any way to decrease that potential still further? We can do that. You see, these positive charges are under the influence of these negative charges and these positive charges. You see, these negative charges produce a negative potential on this charge, and these positive charges produce a positive potential. That means because the negative charges are closer, the negative potential produced by the negative charges will dominate. But this effect can be increased if you can remove these positive charges from here. Now, how will we remove those positive charges? Any suggestions? Can you suggest a way we can remove these positive charges from this end of the neutral conductor? What can we do to remove them? Well, a very simple thing: ground the neutral conductor. If you ground the neutral conductor, negative charges will move from the ground, come in and neutralize those positive charges. You see that? Now, in order to increase the potential back to V, more positive charges need to be given to the conductor. Thus, the presence of the neutral conductor has increased the capacitance of our conductor. Now, what happens if the neutral conductor is grounded? Well, let's ground it. When you ground it, all the positive charges have disappeared. That means the negative potential due to these charges are now have a bigger influence on the positive potential of this conductor. The negative charges from the ground flows in to neutralize the positive charges. This leaves the neutral conductor now negatively charged. Now, this lowers the positive potential of the charged conductor further. Now, that means if you lower the potential, you are increasing the capacitance. You see that? Every time you lower the potential without changing the amount of charge on it, you are increasing the capacitance. Thus, how can you increase the capacitance of a conductor? The capacitance of a conductor can be increased by bringing a neutral grounded conductor near it. So this conductor, the capacitance of this conductor is much greater than its original value. Now, how did we do that? By bringing a neutral grounded conductor near it. Now, the capacitance of the charged conductor can be further increased. There is one more way to increase the capacitance, and that is, you see, the influence of these negative charges are transmitted to the positive charge through this intervening medium. Is that right? You see, the medium plays a part in transmitting electrical influences from one object to the other. Now, from the neutral conductor to the charged conductor, the electrical influences are conveyed or passed on through the intervening medium. Now, if the intervening medium is a much more effective medium, then the electrical influences can be conveyed more effectively. And if you can now use a proper dielectric. What's a dielectric? We talked about that in the last class. A dielectric is an insulator. If you use a proper dielectric, which will transfer the electrical influence in a much more efficient way, then we can reduce the potential of this conductor even more and increase the capacitance. You see how the various things that we have been doing to increase the capacitance. So the capacitance of this conductor can be further increased by using a proper dielectric between the two conductors, which allows electrical influences to travel through it more effectively. Now here I have a dielectric in between. Such an arrangement is called a capacitor. You see, what we have done is we tried our best. We tried all we can to increase the capacitance of this conductor. What was the first thing we did? We brought near it a neutral conductor and grounded it, and then filled the space between them by a very efficient dielectric, which will transmit the electrical influence in a much more efficient way. And this arrangement now is called a capacitor. So what is a capacitor? A capacitor is an arrangement of two conductors separated by a thin dielectric and one of them kept grounded. Well, so we have a capacitor. A capacitor has a capacitance. That means a capacitor. Can you tell me what is a capacitor used for? What is a capacitor used for? Well, if you can answer this question, what is a container used for? A container is used for storing things that it can contain. In the same way, a capacitor is used for storing electric charges. And that's the reason why we try to increase its capacitance. In other words, we want to charge more. We want to store more charges in the conductor or in the capacitor. And look at the symbol we used for a capacitor. A capacitor is represented by this symbol, two parallel lines with the connecting leads. So this kind of an arrangement is called a capacitor. Let's now look at one type of capacitor called a parallel plate capacitor. A parallel plate capacitor. Well, as the name suggests, it tells us that this is made up of two conducting plates, both made of parallel plates. In other words, here I have a metal plate, and if I have one more of these, I couldn't find one like this, so I brought a small one. But remember, the plates of a capacitor both will be the same. So if one is charged and the other is grounded and the two are separated by a proper dielectric, we have a parallel plate capacitor. In a parallel plate capacitor, the two conductors are metal plates separated by a dielectric. A dielectric is characterized by a dielectric constant, and we represent the dielectric constant by the lowercase Greek letter kappa. Kappa. Don't call it K. It looks like K, but we use this as a Greek letter. It's kappa, which has a value 1 for vacuum. But for all practical purposes, we will use the value for air also as 1. For all practical purposes, we use kappa equal to 1 for air. So if I give you a problem in which it says an air capacitor, what does it mean, an air capacitor? An air capacitor is a capacitor in which the dielectric is air. The space between the two conductors is filled with air. Now I have a table of values for kappa for different types of dielectric. Now look at this table. Air is 1.0006. Well, for all practical purposes, we will take it as 1. Now, Pyrex glass, it has the highest value. Well, water has a very high value, but water is not a practical material to be used as a dielectric. So we will not be using water. Well, paper is a good dielectric. Mica is a good dielectric. Bakelite, all of them are commonly used to construct capacitors. All right, let's move on. Now, I told you that the capacitance of a conductor, or now I'm going to say the capacitance of a capacitor. What's a capacitor? A capacitor is an arrangement of two conductors. Now, what are the factors on which the capacitance of a parallel plate capacitor depend on? Can you think about some of the factors on which the capacitance of a parallel plate capacitor depend on? Well, for one thing, you know that the capacitance does not depend on the amount of charge on the capacitor, neither would it depend on the potential of the capacitor. It only depends on the physical dimensions. That means if I make a capacitor, tell me, if I make a capacitor with this kind of plates, another capacitor with this kind of plates, which will have a greater capacitance? Which of them will be able to store more charge? Well, obviously the one that has the larger area. So, capacitance of a capacitor can be increased by increasing the area of the plates. So, the first factor that determines the capacitance of a capacitor is the area A of the plates. The amount of charge that can be stored in a capacitor is directly proportional to its area. Well, here I have a parallel plate capacitor. The amount of charge that can be stored in a parallel plate capacitor is directly proportional to the area of the plates. We represent that by A. Now, what else does it depend on? Tell me, if I bring the plates closer together, if the plates are brought closer together, will it increase or decrease the capacitance? What do you think? Well, if the plates are brought closer together, the effect of the negative charges will be felt more on the positive charge. That means the potential of the charged conductor will be reduced if you bring the neutral conductor as close as possible. That means if the separation between the plates is small, the capacitance will be greater. So the separation D between the plates also is a determining factor on its capacitance. Capacitance of a capacitor is inversely proportional to the separation D between the plates. So we have now capacitance is directly proportional to the area of the plates and inversely proportional to the separation between the plates. What else it depends on? Well, obviously we have one more factor, the dielectric used between the capacitor plates. Is that right? Yes. Okay. The third factor is the dielectric constant kappa of the dielectric separating the two plates. Well, the capacitance is directly proportional to kappa. You use a material with higher dielectric constant, the capacitance will be higher. Now, can you combine all these and write an equation for capacitance of a parallel plate capacitor? Well, yes, we can. C is directly proportional to kappa. It is directly proportional to area of the plates and inversely proportional to the plate separation. That means I can now use a constant. Look at the constant there. Are you familiar with this? Epsilon naught is the constant there. So the capacitance of a parallel plate capacitor equal to kappa epsilon naught A over D, where kappa is the dielectric constant of the dielectric between the plates, A is the area of the plates, and the D is the plate separation. Alright. And you know epsilon naught is the permittivity of free space And what's its value? 8.85 times 10 to the negative 12 farad per meter. Okay, let's do a problem. An isolated spherical conductor of radius 10 centimeter is charged to 2 kilovolt. What is the capacitance of the sphere? What is the charge on the sphere? How does the capacitance change if the sphere is charged to 6 kilovolt? Well, you can actually answer these questions, all of them in one line, if you understand every concept we talked about so far. Now, what is the capacitance of the sphere? What is the equation for the capacitance of a spherical conductor? We just obtained about 10 minutes ago. Capacitance of a spherical conductor is 4 pi epsilon naught r, where r is the radius. The capacitance of a spherical conductor depends only on its radius. So the capacitance of a spherical conductor is 4 pi epsilon naught r, and we got all those values. The radius is 10 centimeter. All these are constant values. That will be 4 pi times epsilon naught, you know what that is, times the radius, and that is 1.1 times 10 to the, what's wrong in here? 10 to the negative 11, not positive 11. You will not get positive 11 if you do this. So the capacitance of our spherical conductor is 1.1 times 10 to the negative 11 farad. Can you imagine something that has as high a farad like this? This is a tremendously high value. Now, can you write this in terms of picofarad? 1.1 times 10 to the negative 11 is the same as, well, this is negative 11. It's the same as 1.1 times, well, it's the same as 11 times 10 to the negative 12, which is 11 picofarad. So the capacitance of the spherical conductor is 11 picofarad. Alright, what's the next one? What is the charge on the capacitor? Well, we know its capacitance. Its capacitance is 11 times 10 to the negative 12, or 1.1 times 10 to the negative 11 farad, and its potential is 2 kilovolt. Now, do you know a relation that exists between capacitance, potential, and the amount of charge? Well, C equal to Q over V. We know C, we know V, we can find Q. Alright, now from this relation C equal to Q over V, we can write Q equal to C times V. We will use this now hundreds of times as we go on. Q equal to C times V, and C is 11 picofarad, 11 times 10 to the negative 11, times V is 2 kilovolt, 2 times 10 to the power of 3 volts, and that will be 2.2 times 10 to the negative 8 coulomb. The amount of charge on that spherical conductor is 2.2 times 10 to the negative 8 coulomb. That is 22 nanocoulomb. Alright, let's do the C part. How does the capacitance change if the sphere is charged to 6 kilovolt? Well, what's the answer? Let me see if you get the right answer. Originally, we charged the conductor to 2 kilovolt, and then the capacitance was 11 picofarad. What will be the capacitance if you charge the conductor to 6 kilovolt? Did you get the answer? Well, What is the answer? There will be no change in the capacitance. Why? Because the capacitance does not depend on the potential. If you want to raise the potential to 6 kilovolt, that is 3 times the original, you've got to give the conductor 3 times the original charge. That means Q divided by V will not change. The capacitance of a conductor does not depend on the amount of charge, nor does it depend on the potential. The capacitance depends only on the physical dimensions of the conductor. Okay, we talked about that. Therefore, the ratio Q over V will remain a constant. Let's do another problem. If a parallel plate capacitor has a 0.15 millimeter separation, that is D, the plate separation, what must be its area for it to have a capacitance of 1 farad? You can see 1 farad is a very high value. B, if the plates are square, what is the length of their sides? Well, we are given the capacitance, you are given the plate separation, and you are not given a dielectric, which means we will use the value of kappa as 1, air capacitor. In a problem like this, if a dielectric is not mentioned, we will assume that it is an air capacitor and we use kappa equal to 1, dielectric constant as 1. So, we've got the capacitance of that capacitor is 1 farad. Epsilon naught is the usual value. The plate separation is 1.5 millimeter, which is 0.15 millimeter, which is 1.5 times 10 to the negative 4 meter. Well, kappa equal to 1. The capacitance of a parallel plate capacitor is kappa epsilon naught A over D. We know the capacitance, we know kappa, we know epsilon naught, we know D, therefore we solve for A. A equal to CD divided by K epsilon naught, and put in all the values. We got all those values there. C is 1, D is 1.5 times 10 to the 4, kappa is 1, and epsilon naught is 8.85 times 10 to the negative 12, and that area is 1.69 times 10 to the 7 meter squared. It's a tremendous amount of area needed to build a capacitor of capacitance 1 farad in order to make so much a storage facility for a large amount of charge. Well, if the plates are made of square, it's a square plate, what is the length and width of, or what's the length of one side? If this area is the area of a square, it will be length multiplied by length, is that right? If area is known, then that area will be equal to L squared for a square. That means L equal to square root of that area. And that means it is 4.11 times 10 to the 3 meter. Now, I included this problem just to impress upon you how big a plate is needed to produce a capacitor of capacitance 1 farad. Now, what is the length of that plate? 4.11 times 10 to the 3 meter is greater than 4 kilometers. So you need a plate greater than 4 kilometers side on a rectangle, and you need 2 plates like that to produce a capacitor of capacitance 1 farad. So 1 farad is a tremendous capacitance. Most of the capacitors that we use in the lab will be much smaller than 1 farad. They will be measured. I will show you some capacitors in a short while as we go on. Okay, let's do another example. A parallel plate capacitor has a capacitance of 2 microfarad and a plate separation of 1.6 millimeter. What is the maximum potential difference between the plates such that dielectric breakdown of air between the plates does not occur? Well, what is the maximum electric field, or what is the electric field required to create that dielectric breakdown? It is 3 times 10 to the 6th. How much charge is stored at this maximum potential difference? What is the charge density on the plates? Well, here we will use information that we have actually obtained from previous lessons and couple it with the concept of capacitance. Alright, what is the first thing that we need to do? What is the maximum potential difference between the plates such that dielectric breakdown of the air between the plates does not occur? Can you think for a while and tell me, if I have 2 metal plates separated by a distance d, there is an electric field between the plates. That means there is a potential difference between the plates. What is the relation connecting the potential difference between the plates, the electric field between the plates, and the plate separation? Can you think of a relation that we did some time ago? Well, delta V equal to negative E times D. Is that right? Yes. E equal to negative delta V over delta X. That is a relation. We have been using that many times. So, pick the data. Capacitance of the capacitor is 2 times 10 to the negative 6 farad, 2 microfarad. Epsilon naught is the usual value. The plate separation is 1.6 millimeter, which is 1.6 times 10 to the negative 3 meter. And kappa for air is 1. For dielectric breakdown to occur, the electric field must be at least this. This is the minimum electric field required to produce dielectric breakdown. So this is the electric field. Now, here I have the situation. These are the capacitor plates. The plate separation is 1.6 meter. The electric field between the plates is 3 times 10 to the 6th. If the electric field increases any further, there will be dielectric breakdown in between. Now, E equal to V over D. I have done away with the negative sign. You see that? There's no need for the negative sign. We only need the magnitude. So we have E equal to V over D, or V equal to E times D. Remember, this is the same relation we used earlier. E equal to delta V divided by delta X. E equal to potential difference divided by the plate separation. So V equal to E times D. And E is 3 times 10 to the 6th. D is 1.6 times 10 to the negative 3. And that is 4,800 volts. So the maximum potential difference you can apply between the 2 plates without causing a dielectric breakdown is 4,800 volts. If you increase the potential difference from this value, the electric field will increase, and that will result in dielectric breakdown. And remember, the capacitance will no longer work if there is a dielectric breakdown. The space between the 2 plates must be an insulator for the capacitor to function normally. how much charge is stored at this maximum potential difference? Well, we know the capacitance, we know the potential difference. Well, do we need anything else to calculate the amount of charge? Q equal to CV, is that right? Because the definition of C is C equal to Q over V, therefore C equal to Q over V, therefore Q equal to C times V. We got a C, 2 times 10 to the negative 6. We just calculated V, 4,800 volts. Therefore, the amount of charge on the capacitor at that time is 0.0096 coulombs. Again, you notice that a coulomb is a very large amount of charge. What is the charge density on the plate? Now, how do you find that? The charge density. Well, you know that E, the electric field between two parallel plates, have you forgotten that? The electric field at any point between two parallel plates is sigma over epsilon naught. We know the electric field 3 times 10 to the power 6. And of course we know epsilon naught, we know it every time. Therefore sigma equal to E times epsilon naught, that is 3 times 10 to the 6 times epsilon naught, gives you 2.66 times 10 to the 5 Newton per meter square. And that is the charge density on the plates. Well, let me ask you one thing. What is a capacitor used for? Think about that. I will try and show you a couple of capacitors and show you what it is used for. Have you thought about the question of what a capacitor is used for? Well, knowing that a capacitor is a device for storing charge. Well, if you store charge, you must be able to use it for something. Is that right? Yes. So, a capacitor may be a device that after storing charge, you see the process of storing charges in a capacitor is called charging a capacitor. And once you charge it, you may be able to remove that charge from the capacitor for some useful purpose. You can discharge the capacitor. You see, in the olden days, I don't know if any one of you remember, but I remember a lot of things that happened 10, 20, 30, 40, 50 years ago. An electronic flash that when you turn on, it will begin to charge, and if you listen to it carefully, you can hear a key sound. Now what happens is, when you turn on the flash, it connects the battery inside to a capacitor, and the capacitor will store a lot of electric charge in it. And then when you press the camera on, this capacitor will suddenly and quickly discharge all that stored charge through a bulb to produce a bright flash. You see that? Charge the capacitor when you want to store a large amount of charge. Discharge it when you want a large amount of current flowing in a very short time. That is what you want in an electronic flash. Large amount of charge flowing in a very short time. Now, is there anywhere else capacitors are used? If you open up your computers or any of the electronic gadgets, there are capacitors there. You see, a capacitor can be actually used as a smoothing circuit. All the electronic equipment that we have are meant to work on direct current. And you plug it into an alternating current socket. Well, that means your equipment has to convert the alternating current that goes up and down, a pulsating current, into a direct current that remains steady. And a capacitor plays a big role in it. The capacitor will store all the charges during that up and down oscillations of the AC, and it will discharge in a steady manner. You see, a lot of electronic circuits uses capacitors. Now look at this electronic circuit. Now there is a capacitor here, and this is the capacitor. Have you seen that? This is the capacitor. What is the value of that capacitor? It is a 1000 microfarad capacitor. And look at the symbol given there. The symbol of the capacitor is given there. Well, another capacitor that I have here is this. This is a very large capacitor is actually. Now, can you read what the value of the capacitance is? It is 25,000 microfarad. Now, this can store a large amount of charge. Well, let me see if I can demonstrate the process of charging and discharging. Well, in order to charge a capacitor, what all I need to do is, you understand this, don't you? This is a bike battery. Well, what I'm going to do is, I don't have to do it for a long time. I connect the positive of the capacitor to the positive of the battery and the negative to the negative. Now, what this does is, the battery sends electric charges to the capacitor. So electric charges are now removed from the battery and stored in the capacitor. Now, if I want to discharge it, well, I have a bulb here. If I connect this capacitor to the bulb, well, I hope I don't blow this bulb up. Now, look at this. There you are. You see that bulb? Well, that means all the charges have been used up. Now, if I want to light the bulb again, I can go and charge that again. Well, I need to positive here and negative here. I need only touch it, and I can go and light the bulb again. You see that? So, this is a very useful device. I can charge and then use it. I can charge and use it, and so on. So a capacitor is a device for storing electrical charges. You can charge a capacitor and discharge a capacitor to derive the charge from it. Now, how do we make a capacitor as big as that? Now, if you notice, I broke a capacitor up. This is a capacitor. In fact, I didn't do it. One of my students about 2 years ago did this. He brought this so that everybody can see. You see, this is a capacitor plate. It is actually aluminum foil. And you see how it is arranged? It is rolled so that the dielectric, you see, you have a dielectric in between. A thin sheet of paper, and you roll it up. Why do we do this? To increase the plate area. So you can construct your capacitor like this. You can use a very large area of the conducting plate, a very thin plate, and then separate them by a thin dielectric. We can construct very large capacitors. So we talked about capacitors, the capacitance of the capacitor, and what a capacitor is used for. And I'm going to stop this lesson here. I will continue with the energy of a capacitor a little while later. Alright? These charges will induce positive charges on the spiked conductors. So there will be induced charges on the conductors, and because of the pointed ends, all those induced charges will be concentrated at the pointed ends, and the concentration of these positive charges will gradually neutralize all the negative charges in the cloud. So what does the lightning arrestor do? it will gradually neutralize all the buildup of charges, thereby preventing a discharge. So this is a very useful thing to do for very tall buildings, and in many places in the world I have actually seen lightning conductors. I haven't seen them in Florida, although Florida is called the lightning capital of the world. Well, let me see if I can show you a similar